Imagine for a moment that you're standing on a beach at night. The sand is cool beneath your feet, the waves crash in rhythmic certainty, and above you, the cosmos unfolds in all its terrifying magnificence. Billions upon billions of stars pierce the darkness, each one a sun, many harboring worlds we'll never touch, never see, never know. Now ask yourself this: what if you could hold all of that in the palm of your hand? What if humanity could harness not just the energy of our sun, not just our planet, but entire galaxies? What if we could become something so powerful, so technologically advanced, that we would be indistinguishable from gods to our ancestors? This isn't science fiction. This is the Kardashev scale, and it measures something profound: the technological advancement of civilizations based on their energy consumption. And here's the disturbing truth: by this measure, we aren't even a full civilization yet. We're still crawling in the cosmic dirt, reaching for something we can barely comprehend. In 1964, a Soviet astronomer named Nikolai Kardashev was grappling with a problem that had haunted humanity since we first looked up at the stars and wondered if we were alone. How do you search for alien civilizations? More importantly, how do you recognize one if you find it? Kardashev was working on the Soviet SETI program, searching for signals from the cosmos, and he realized that any civilization capable of sending signals across interstellar space would need tremendous amounts of energy. So he did something brilliant and simple. He created a scale, not based on culture, not based on politics or philosophy, but based on the one thing that defines technological progress more than anything else: energy. The ability to harvest it, store it, and use it. Energy is everything. It's the currency of the universe, the fundamental resource that separates a species huddling around campfires from one that can reshape reality itself. Kardashev proposed 3 types of civilizations. Type 1. A planetary civilization that can harness all the energy available on its home planet. Type 2. A stellar civilization that can harness all the energy of its star. Type 3. A galactic civilization that can harness the energy of an entire galaxy. When you first hear this, it might sound like a simple progression, like climbing stairs. But each step is a chasm so vast, so incomprehensibly large, that it makes the gap between a single-celled organism and a human being look trivial. Each level requires not just incremental improvement, but fundamental transformations in technology, society, and our understanding of physics itself. Let's start with Type 1, because this is the first rung on the ladder, the one we're desperately trying to reach. A Type 1 civilization has complete mastery over its planet. They control the weather, they prevent earthquakes, they mine the oceans, the atmosphere, and the planetary crust with perfect efficiency. Every drop of geothermal energy, every gust of wind, every ray of sunlight that touches their world is captured and utilized. Think about that for a moment. Picture Earth, but with zero waste, zero inefficiency. Hurricanes are dissipated before they form, or their energy is captured and stored. Volcanic eruptions are predicted centuries in advance and either prevented or their energy harvested. The entire planet becomes a machine, perfectly optimized for energy collection and use. Carl Sagan, the great science communicator who made the cosmos accessible to millions, later refined the Kardashev scale to include intermediate values. By his calculations, humanity in the 1970s was approximately a Type 0.7 civilization. We've improved since then. As of the early 21st century, various estimates place us somewhere between Type 0.72 and 0.73. We're not even Type 1 yet. We're a Type 0 civilization, still burning dead plants and animals from millions of years ago, still fighting wars over patches of land and barrels of oil, still poisoning our own atmosphere with the waste products of our primitive energy systems. Here's a fact that should make you pause. Humanity currently uses about 18 terawatts of power continuously. That's 18 trillion watts, running every second of every day. It sounds like a lot, doesn't it? But to become a Type 1 civilization, we would need to use approximately 175,000 terawatts. roughly 10,000 times more energy than we currently consume. And that's just type 1, just planetary mastery. We're not even close. Physicist and futurist Michio Kaku estimates that, at our current rate of progress, it will take us roughly 1 to 200 years to reach type 1 status. 200 years. That's assuming we don't destroy ourselves first, assuming we can overcome the challenges of climate change, resource depletion, and our own tribalistic tendencies that keep us divided into competing nations rather than united as a species. But let's be optimistic for a moment. Let's imagine we make it. Picture Earth in 200 years. Fusion power plants, landscape. Their clean reactions producing limitless energy from seawater. Solar arrays in orbit beam power down to receivers on the surface. The Sahara Desert is covered in solar panels. The ocean studded with wave energy converters and offshore wind farms. Every building is a power generator, its windows made of transparent solar cells, its walls embedded with thermoelectric generators that convert heat differentials into electricity. Humanity has become a single, unified civilization, because you can't achieve type 1 while fighting among yourselves. The energy requirements alone demand global cooperation, unified infrastructure, and the pooling of resources on a planetary scale. Ask yourself this: do you think we can do it? Can we, as a species, overcome our differences long enough to achieve this? Can we stop seeing ourselves as Americans, Chinese, Europeans, Africans, and start seeing ourselves as Earthlings, as one civilization among potentially countless others in the cosmos? Now let's talk about type 2, and this is where things start to become truly alien to our current understanding. A type 2 civilization has complete mastery over its star. Not just the light that happens to fall on their planet, but all the energy the star produces, radiating out in every direction. Our sun, Sol, produces about 386 billion megawatts of power every second. Most of it shoots off into empty space, wasted, heating nothing but the cosmic void. A Type 2 civilization would consider this intolerable. They would capture it all. Here's something that should fundamentally shake your perception of solid reality. Atoms, the building blocks of matter, are almost entirely empty space. If an atom were the size of a football stadium, its nucleus would be a pea on the 50-yard line, and its electrons would be tiny specks orbiting somewhere up in the stands. Everything between is nothing, just empty space. You are, at the atomic level, almost entirely empty. The chair you're sitting on, the ground beneath your feet, the walls around you, all of it is 99.9999999% empty space. The only reason you don't fall through the floor is electromagnetic repulsion between the electron clouds of atoms, forces acting across emptiness to create the illusion of solidity. On a cosmic scale, this emptiness becomes even more profound. If you removed all the empty space from all the atoms and all the humans on Earth, the entire human race would fit into a volume the size of a sugar cube. The universe is not mostly stuff with some empty space between. It's mostly nothing, with occasional condensations of matter and energy scattered across the void like rare islands in an infinite ocean. But even calling it empty space doesn't capture the strangeness. Quantum physics has revealed that the vacuum of space seethes with activity. Virtual particles constantly pop into and out of existence. Matter and antimatter pairs created from pure energy, existing for the briefest instant before annihilating each other and vanishing back into the void. The vacuum isn't empty. It's a roiling foam of quantum fluctuations, reality bubbling and churning at scales too small and too brief for us to directly observe. Some physicists speculate that the entire universe might be one such quantum fluctuation, a random bubble that happened to inflate into everything we know. If true, there could be countless other universes, other bubbles in an infinite quantum foam, each with potentially different laws of physics, different fundamental constants, different realities altogether. This is the multiverse hypothesis, and while it remains speculative, it's grounded in serious physics and mathematics. Take a moment to wonder. If there are infinite universes with infinite variations, does that mean every possible version of reality exists somewhere? Does that mean there's a universe where you made every different choice, lived every different life? Let's talk about something most people have heard of but few truly understand: black holes. These cosmic monsters form when massive stars, much larger than our sun, reach the end of their lives and collapse under their own gravity. When a star runs out of fuel, the outward pressure from nuclear fusion that has supported it against gravitational collapse suddenly ceases. For stars above a certain mass, nothing can stop the collapse. The star's core implodes, and if enough mass is present, it collapses past the point where even atomic structure can resist. It keeps collapsing past neutron degeneracy, past every known physical barrier, becoming a point of infinite density called a singularity, surrounded by an event horizon, a boundary beyond which nothing, not even light, can escape. The gravity is so intense that it literally tears holes in the fabric of spacetime. Hence the name, black hole. The event horizon of a black hole is the point of no return. Cross this invisible boundary and your fate is sealed. You will fall toward the singularity, and nothing in the universe can save you. Not rocket engines, not nuclear explosions, nothing. The escape velocity exceeds the speed of light, and since nothing can travel faster than light, escape becomes physically impossible. But here's where it gets truly mind-bending. Due to time dilation effects predicted by Einstein's general relativity, time behaves strangely near a black hole. If you watched someone fall toward a black hole's event horizon, you would never see them cross it. Time would slow down for them from your perspective, their descent becoming slower and slower, their image freezing at the horizon and gradually redshifting and fading as the photons climbing out of the gravity well lose energy. From their perspective, however, they would cross the horizon in finite time, likely without even noticing the exact moment of crossing. Time itself becomes relative, different observers experiencing different temporal realities. If you were unfortunate enough to fall into a black hole, you would experience something called spaghettification. The gravity differential between your head and feet would become so extreme that you would be stretched like taffy, pulled into a long thin noodle of atoms before being torn apart completely. For smaller black holes, this would happen before you reached the event horizon. For supermassive black holes, those millions or billions of times the mass of the sun, the tidal forces at the event horizon are actually gentler, and you might cross the boundary intact, only to be spaghettified later as you approach the central singularity. Either way, your fate would be to become part of the black hole, your information seemingly lost forever. This created a paradox in physics because quantum mechanics says information cannot be destroyed, while black holes apparently destroy it. Stephen Hawking spent decades working on this problem, eventually proposing that black holes emit radiation, now called Hawking radiation, through quantum effects at the event horizon. Over unimaginable spans of time, black holes can evaporate completely, theoretically releasing the information they consumed, though in a scrambled form that would be impossible to decode. At the center of nearly every large galaxy, including our Milky Way, lurks a supermassive black hole. Our galaxy's central black hole, called Sagittarius A star, weighs about 4 million times the mass of our Sun. Despite this immense mass, it's relatively quiet, consuming only a trickle of matter. But some supermassive black holes actively feed, drawing in vast quantities of gas and dust that form an accretion disk, a swirling maelstrom of superheated material spiraling toward oblivion. The friction in these accretion disks heats the material to millions of degrees, causing it to emit intense radiation across the electromagnetic spectrum. These feeding black holes, called active galactic nuclei or quasars, can outshine their entire host galaxies, becoming the brightest objects in the universe. Some quasars blast out jets of particles and energy at nearly the speed of light, jets that extend for hundreds of thousands of light years into intergalactic space. The energy released by these cosmic engines defies comprehension, trillions of times the output of our Sun, powered by matter being torn apart and consumed by insatiable gravity. Now pause and ask yourself, what would happen if you could visit a black hole up close? What would you see looking back at the universe as time dilation took hold? Would you watch the universe age and die and fast forward as you fell, seeing stars burn out and galaxies fade? Or would the redshift rob you of the view, the universe fading to darkness as photons lost their energy climbing out of the gravity well to reach your eyes. Let's shift perspective and consider dark matter, one of the deepest mysteries in cosmology. When astronomers studied the rotation of galaxies, they discovered something impossible. Galaxies spin, rotating like great cosmic pinwheels, and by measuring the speed of stars at different distances from the galactic center, scientists can calculate how much mass the galaxy contains. But the observations didn't match expectations. Stars far from the galactic center were moving too fast. According to the visible matter in galaxies, these outer stars should be moving slower, and many should be flung off into intergalactic space by centrifugal force. But they're not. Something invisible, something that doesn't emit or absorb light, is providing additional gravitational force, holding galaxies together. This invisible stuff is called dark matter, and it outweighs all the normal matter in the universe by a factor of about 5 to 1. Everything you can see, every star and planet and gas cloud, all the matter made of atoms, constitutes only about 17% of the total matter in the universe. The rest is dark matter, invisible and mysterious, interacting with normal matter only through gravity. Scientists have searched for dark matter particles for decades, building incredibly sensitive detectors deep underground to shield them from cosmic rays and other interference. So far, dark matter has eluded direct detection. We know it's there because we can see its gravitational effects. We can map its distribution by observing how it bends light from distant galaxies through gravitational lensing. We can see how it shaped the large-scale structure of the universe, providing the gravitational scaffolding along which normal matter collected to form galaxies and galaxy clusters. But we don't know what it's made of. The leading candidates are exotic particles that don't interact electromagnetically, passing through normal matter like ghosts, almost never colliding with atoms. Imagine that right now, as you exist in this moment, countless dark matter particles are streaming through your body, through the earth, through everything, completely unimpeded, invisible and intangible. The universe is far stranger than it appears. But dark matter isn't even the strangest component of the universe. That distinction belongs to dark energy, something even more mysterious and counterintuitive. In the late 1990s, astronomers studying distant supernovae made a shocking discovery. By using certain types of supernovae as standard candles, objects whose intrinsic brightness is known, astronomers can calculate their distance by measuring how bright they appear from Earth. When they did this for very distant supernovae, they discovered these explosions were dimmer than expected, meaning they were farther away than calculations based on the universe's age and expansion rate suggested. The only way to explain this was if the universe's expansion was accelerating, speeding up over time rather than slowing down as expected. This was completely unexpected. Gravity, the dominant force on cosmic scales, should cause the universe's expansion to slow down over time, the mutual gravitational attraction of all matter acting as a cosmic brake. But observations showed the opposite. Something was pushing the universe apart, causing space itself to expand faster and faster. This mysterious force was named dark energy, and it's even more abundant than dark matter. Current estimates suggest dark energy makes up about 68% of the universe's total energy density. Dark matter accounts for about 27%. Normal matter, everything made of atoms, all the stars and planets and people, constitutes a mere 5%. We are a tiny minority in a universe dominated by invisible components we barely understand. Dark energy behaves like a property of space itself, a kind of anti-gravity that grows stronger as space expands. The more space there is, the more dark energy there is, driving acceleration in a runaway feedback loop. If this continues, the ultimate fate of the universe is cold and lonely. In trillions of years, the accelerating expansion will carry distant galaxies beyond the cosmic horizon, their light redshifted into oblivion. Eventually, only our local group of gravitationally bound galaxies will remain visible. After even longer timescales, stars will burn out, galaxies will fade to black, and the universe will approach a state of maximum entropy called heat death, where no free energy remains to do work, and nothing can happen. The universe will be cold, dark, and essentially dead, a sea of radiation and isolated particles separated by ever-expanding voids. Have you considered the nature of time itself? We experience time as flowing from past to future, an arrow pointing in one direction. But physics doesn't inherently contain this arrow. The fundamental equations of physics work equally well running forward or backward in time. The arrow of time emerges from entropy, the second law of thermodynamics, which states that closed systems tend toward disorder. The universe started in a highly ordered state at the Big Bang and has been running downhill toward disorder ever since. Entropy always increases, and this gives time its direction. But why did the universe start in such a highly ordered state? That's one of the deepest questions in cosmology, and nobody really knows the answer. Some theorists speculate that what we call the Big Bang might not have been the absolute beginning, but rather a transitional phase from some prior state. Perhaps the universe goes through cycles of expansion and contraction, bouncing eternally between big bangs and big crunches. Or perhaps our universe budded off from a parent universe, inflation creating a new bubble of space-time that became everything we know. These ideas remain speculative, but they point to the profound mysteries still lurking at the foundations of cosmology. Light, that most familiar phenomenon, holds secrets that challenge intuition. Light travels at exactly 299,792,458 meters per second in vacuum. This isn't just a speed limit for light. It's the speed limit of causality itself, the maximum rate at which cause and effect can propagate through the universe. Nothing with mass can reach this speed because doing so would require infinite energy. As objects with mass accelerate, they gain relativistic mass, becoming harder and harder to accelerate further. Approaching the speed of light, the energy required for further acceleration approaches infinity. Light can travel at this cosmic speed limit because photons have no rest mass. They always travel at exactly this speed, never faster, never slower. From a photon's perspective, if it could have a perspective, no time passes during its journey. A photon emitted from a distant quasar billions of light-years away experiences its entire journey instantaneously from its own reference frame. It's created and absorbed in the same moment, even though billions of years pass from our perspective. Time dilation at light speed becomes infinite, compressing the photon's journey to a single instant. This leads to a profound realization. When you look at distant objects in space, you're looking back in time. The sun is about 8 light minutes away, meaning when you see the sun, you're seeing it as it was 8 minutes ago. If the sun suddenly vanished, we wouldn't know for 8 minutes. We'd still see it shining in the sky, still feel its warmth, because the light and heat from that final moment would take 8 minutes to reach us. The nearest star system, Alpha Centauri, is over 4 light-years away. We see it as it was 4 years ago. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. When you see a photograph of Andromeda, you're seeing it as it was 2.5 million years ago, when our ancestors were primitive hominids just learning to use stone tools. The most distant galaxies we've observed are over 13 billion light-years away, meaning we see them as they were when the universe was less than a billion years old, young galaxies forming in the cosmic dawn. We can never see these galaxies as they are now. By the time their light reaches us, billions of years have passed for them, and they've likely evolved into mature galaxies completely different from the young galaxies we observe. Consider the cosmic microwave background, perhaps the most important discovery in cosmology. In the 1960s, 2 scientists at Bell Labs, Arno Penzias and Robert Wilson, were testing a sensitive radio antenna and kept detecting a persistent noise, a faint hiss coming from all directions in the sky. They cleaned the antenna, removed bird droppings, checked every component, but the signal remained. What they discovered was the afterglow of the Big Bang itself, radiation that has traveled across the universe for over 13 billion years, stretched by cosmic expansion from visible light into microwave wavelengths. This cosmic microwave background radiation fills the entire universe, a nearly uniform bath of photons at a temperature of just 2.7 degrees above absolute zero. These photons were released about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, making the universe transparent for the first time. Before this moment of recombination, the universe was opaque, a hot plasma where photons constantly scattered off free electrons. After recombination, photons could travel freely, and those photons have been traveling ever since, filling space with fossil radiation from the infant universe. The cosmic microwave background isn't perfectly uniform. It contains tiny temperature fluctuations, variations of only a few parts in 100,000, but these tiny fluctuations were the seeds from which all cosmic structure grew. Regions that were slightly denser attracted more matter through gravity, growing denser still, eventually collapsing to form the first stars and galaxies. By mapping the pattern of fluctuations in the cosmic microwave background, scientists can test models of cosmic inflation and determine fundamental parameters of the universe like its age, composition, and geometry. These observations have confirmed that the universe is flat on large scales, meaning parallel lines remain parallel forever rather than converging or diverging as they would in curved space. This flatness is itself remarkable and requires fine-tuning of conditions in the early universe, one of many coincidences that make our existence possible. Speaking of coincidences, let's explore the anthropic principle and the fine-tuning problem. The laws of physics contain various fundamental constants, numbers that determine the strength of forces and the masses of particles. These constants could, in principle, have any value. But if you changed most of them by even tiny amounts, the universe would become hostile to life. If the strong nuclear force were slightly weaker, atomic nuclei couldn't hold together, and complex atoms wouldn't exist. If it were slightly stronger, hydrogen would rapidly fuse into heavier elements, and stars couldn't form. If gravity were a bit stronger, stars would burn out too quickly for life to evolve. If it were weaker, stars might never ignite nuclear fusion. If the electromagnetic force had a different strength, chemistry would be impossible. The list goes on. The universe appears fine-tuned for life, or at least for the kind of complex chemistry that makes life possible. Why? One explanation is the multiverse. If there are countless universes with randomly varying constants, most would be sterile, but a few would have the right combination to support life. We exist in one of those rare universes because we couldn't exist in any other kind. This is the anthropic principle. We observe the universe to be compatible with our existence because if it weren't, we wouldn't be here to observe it. Ask yourself now, does the fine-tuning of cosmic constants suggest purpose, or is it simply selection bias, our existence filtering the observations we can make? If you believe in purpose, who or what set those constants so precisely? If you believe in the multiverse, how do you reconcile the existence of countless unobservable universes? These questions venture into philosophy as much as physics, but they arise naturally from scientific observations. Let's ground ourselves back in observable phenomena and discuss stellar evolution. Stars are born in nebulae, vast clouds of gas and dust floating in interstellar space. When a region of a nebula becomes dense enough, perhaps triggered by the shock wave from a nearby supernova, it begins to collapse under its own gravity. As it collapses, it heats up, the gravitational potential energy converting to thermal energy. When the core becomes hot and dense enough, hydrogen nuclei overcome their electromagnetic repulsion and fuse together, forming helium and releasing tremendous energy. A star is born, entering the main sequence phase where it will spend most of its life fusing hydrogen into helium. Our Sun has been doing this for about 4.6 billion years and will continue for another 5 billion years or so. But all stars eventually run out of hydrogen fuel in their cores. What happens next depends on the star's mass. For stars like the Sun, the core contracts and heats up when hydrogen is exhausted, and a shell of hydrogen around the core begins fusing. The star expands enormously, becoming a red giant. In this phase, the Sun will swell to engulf the orbits of Mercury and Venus, possibly reaching Earth's orbit. The Sun's outer layers will cool and redden, but its luminosity will increase 1,000-fold. The Earth, if not consumed entirely, will be sterilized, its atmosphere stripped away, its oceans boiled into space, leaving a scorched cinder orbiting a bloated dying star. Eventually, the core becomes hot enough to fuse helium into carbon and oxygen. For a star like the Sun, this is as far as fusion goes. The core lacks the mass to reach the temperatures needed to fuse carbon. The star puffs off its outer layers in a planetary nebula, leaving behind a dense core called a white dwarf. A white dwarf is incredibly dense, packing roughly the mass of the Sun into a sphere the size of Earth. A teaspoon of white dwarf material would weigh several tons on Earth. White dwarfs shine with residual heat, gradually cooling over billions of years until they fade into black dwarfs, cold dark cinders floating in space. No white dwarf has yet cooled to become a black dwarf because the universe isn't old enough. For stars much more massive than the Sun, the ending is far more dramatic. These stellar giants can continue fusing heavier elements in their cores. Carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron. Each stage produces less energy and lasts a shorter time. The final iron core forms in a matter of days. But iron is the dead end. Fusing iron consumes energy rather than releasing it. The iron core grows until it reaches a critical mass, about 1.4 times the mass of the Sun. At that point, nothing can support it against gravity. The core collapses catastrophically in less than a second, neutrons forming as protons and electrons are crushed together. The collapse halts when the core reaches nuclear density, and the infalling material rebounds, generating a shock wave that tears the star apart in a supernova explosion. For a brief time, a single star can outshine an entire galaxy of hundreds of billions of stars. The explosion forges elements heavier than iron through rapid neutron capture and scatters them into space, enriching the interstellar medium with the raw materials for new stars and planets. Every atom in your body heavier than hydrogen was forged in the core of a star or in a supernova explosion. The calcium in your bones, the iron in your blood, the oxygen you breathe, the carbon that forms the backbone of organic molecules, all of it was created in stellar furnaces and scattered into space when those stars died. You are literally made of stardust, the remnants of dead stars that lived and died billions of years ago. When you breathe, you inhale atoms that were once part of distant stars. When you exist, you carry forward the legacy of cosmic evolution, the universe arranged in such a way that it has become conscious of itself. Think about that the next time you look in a mirror. You're not just a person. You're a way the universe is experiencing itself. After a supernova, what remains of the core depends on its mass. If it's between about 1.4 and 3 solar masses, it becomes a neutron star, an object so dense that atomic structure collapses entirely. Electrons and protons merge to form neutrons, and the entire star becomes essentially a giant atomic nucleus about 10 to 20 kilometers across but weighing more than the Sun. Neutron stars are the densest objects in the universe aside from black holes. A teaspoon of neutron star material would weigh 1 billion tons on Earth. The gravity at the surface is so intense that if you dropped an object from 1 meter up, it would hit the surface at millions of kilometers per hour. If you could somehow stand on a neutron star, you'd be instantly compressed into a layer of atoms just a few atoms thick. Some neutron stars are magnetars, possessing magnetic fields a quadrillion times stronger than Earth's. These are the strongest magnetic fields known to exist in the universe. A magnetar's magnetic field is so intense that it warps the very atoms in its vicinity, stretching them into elongated spindles. If a magnetar existed halfway between Earth and the Moon, its magnetic field would erase every credit card and hard drive on Earth and pull the iron from your blood. Fortunately, the nearest known magnetar is thousands of light years away. Neutron stars often spin rapidly, some rotating hundreds of times per second. When they emit beams of radiation from their magnetic poles, these beams sweep across space like a lighthouse beam. If one sweeps across Earth, we detect regular pulses of radiation. These pulsing neutron stars are called pulsars, and they're among the most precise clocks in the universe. Some pulsars are so regular that they rival atomic clocks in precision. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, who initially wondered if the regular signals might be communications from an alien civilization. She jokingly called the first pulsar LGM-1 for little green men. But further discoveries showed pulsars were natural phenomena. Neutron stars spinning in the cosmic void, their death throes creating cosmic lighthouses. If the stellar remnant after a supernova is more than about 3 solar masses, no known force can halt the gravitational collapse. The neutron star collapses into a black hole, and we've come full circle back to those cosmic monsters. But let's venture further into exotic phenomena. Some theoretical models predict objects even stranger than black holes. Cosmic strings, for instance, are hypothetical one-dimensional defects in spacetime, impossibly thin but incredibly dense, stretching across cosmic distances. If they exist, they formed in the first moments after the Big Bang as the universe cooled and underwent phase transitions, like cracks forming in ice as water freezes. A cosmic string just a few miles long would outweigh the Earth. If a cosmic string passed through the solar system, its gravitational field would be so intense and localized that it could tear planets apart. Some physicists have speculated that cosmic strings could be used for time travel, their extreme gravity warping spacetime enough to create closed time-like curves, paths through spacetime that loop back on themselves, theoretically allowing travel to the past. However, no cosmic strings have been detected, and they may not exist at all. They remain in the realm of speculation, mathematical possibilities that may or may not be realized in nature. Another theoretical prediction involves something called Hawking radiation, named after Stephen Hawking, who predicted it in 1974. According to quantum field theory, the vacuum of space constantly produces virtual particle pairs, a particle and its antiparticle, which normally annihilate each other almost instantly. But near a black hole's event horizon, something strange can happen. If a particle-antiparticle pair forms right at the horizon, one might fall into the black hole while the other escapes. From an outside perspective, the black hole has emitted a particle. This is Hawking radiation. The emitted particle carries energy, and since energy must be conserved, the black hole loses mass. Over unimaginable timescales, this causes black holes to evaporate. A solar mass black hole would take longer than the current age of the universe to evaporate significantly, but smaller black holes would evaporate faster. A black hole with the mass of a mountain would evaporate in roughly the current age of the universe. As a black hole evaporates, it gets hotter and radiates faster, leading to a runaway process that ends in a final explosion. In the last second of a black hole's life, it releases energy equivalent to millions of nuclear bombs. No one has ever observed this because stellar mass black holes are far too large to have evaporated yet. But in the far future, when the stars have burned out and the universe grows cold, evaporating black holes might be the last fireworks in a dying cosmos. Let's turn our attention to the large-scale structure of the universe. If you could zoom out and see the universe from beyond, you'd see that galaxies aren't distributed randomly. They form a cosmic web, a vast network of filaments and walls surrounding enormous voids. Galaxies cluster along the filaments, drawn together by the gravity of dark matter. The voids, regions hundreds of millions of light-years across, contain very few galaxies. This structure arose from the tiny density fluctuations in the early universe. Denser regions attracted more matter, growing denser still, while less dense regions lost matter to their surroundings, becoming voids. The result is a sponge-like structure, a cosmic foam with galaxies concentrated in the bubble walls and vast emptiness in the bubbles themselves. One of the strangest features in this cosmic web is the Great Attractor, a gravitational anomaly located roughly 150 million light-years from Earth. Our Milky Way galaxy, along with hundreds of thousands of other galaxies in our cosmic neighborhood, is being pulled toward the Great Attractor at speeds of several hundred kilometers per second. For decades, The great attractor's nature remained mysterious because it lies in the zone of avoidance, a region of the sky obscured by the Milky Way's disk, making it difficult to observe. Eventually, astronomers determined that the great attractor is itself being pulled toward an even larger structure called the Shapley supercluster, a collection of galaxy clusters so massive its gravity influences structures hundreds of millions of light years away. We're falling through space at enormous speeds toward something vast and distant, part of motion set in motion billions of years ago by the gravitational pull of immense cosmic structures. Ask yourself, does knowing we're falling through space at hundreds of kilometers per second change how you feel about your place in the universe? Do you feel the motion? Of course not. You never feel uniform motion, only acceleration, only changes in motion. Einstein's relativity tells us that all non-accelerating reference frames are equally valid. From one perspective, we're falling toward the Shapley supercluster. From another, we're at rest and the supercluster is approaching us. Neither perspective is more correct than the other. Motion is relative, and only changes in motion, accelerations, have absolute meaning. This relativity of motion is one of the foundations of physics, yet it contradicts our everyday intuition. Now let's discuss gravitational waves, ripples in the fabric of spacetime itself. Einstein predicted their existence in 1916 as a consequence of general relativity. When massive objects accelerate, they create disturbances in spacetime that propagate outward at the speed of light, stretching and compressing space as they pass. For decades, gravitational waves remained undetected because they're incredibly weak. Even cataclysmic cosmic events produce waves that barely affect spacetime when they reach Earth. But in September 2015, the LIGO detectors, enormous laser interferometers designed to detect minute changes in distance, observed gravitational waves for the first time. The signal came from two black holes spiraling together and merging about 1.3 billion light-years away. As the black holes orbited each other, their mutual gravity became so intense they generated gravitational waves that carried energy away from the system, causing the orbit to shrink. The black holes spiraled closer and closer, orbiting faster and faster, until they merged in a violent collision that released more energy in a fraction of a second than all the stars in the observable universe emit in that same time. The gravitational waves from this merger traveled across space for over 1 billion years before reaching Earth, where they caused the LIGO detector's mirrors to shift by a distance smaller than the width of a proton. That humans can detect such tiny distortions is itself a marvel of engineering and physics. Since that first detection, dozens more gravitational wave events have been observed, including collisions between neutron stars. When two neutron stars merge, they don't just produce gravitational waves, they also emit electromagnetic radiation across the spectrum. In August 2017, observatories around the world detected both gravitational waves and light from a neutron-star merger. This event confirmed that neutron-star collisions are a major source of heavy elements like gold and platinum. The collision created a kilonova, an explosion that forged vast quantities of heavy elements through rapid neutron capture and scattered them into space. Much of the gold and platinum on Earth likely came from such collisions billions of years ago, before the solar system formed. Your wedding ring, if it's gold, contains atoms forged in the death throes of colliding neutron stars. Let's change scale dramatically and talk about quantum mechanics, the physics of the very small. At scales smaller than atoms, reality becomes profoundly weird. Particles don't have definite positions or velocities until they're measured. Instead, they exist in quantum superpositions, being in multiple states simultaneously until an observation collapses the superposition into a definite state. A quantum particle can be here and there at the same time, traveling multiple paths simultaneously. The famous double-slit experiment demonstrates this. Fire electrons one at a time at a barrier with two slits, and they create an interference pattern on a detector screen, as if each electron passes through both slits and interferes with itself. But if you place a detector at the slits to see which slit each electron passes through, the interference pattern disappears, and the electrons behave like classical particles, each passing through one slit or the other. The act of measurement changes the outcome. Observation affects reality at the quantum level. This is deeply unsettling. It suggests that reality at its most fundamental level is not deterministic but probabilistic. Einstein famously disliked this aspect of quantum mechanics, saying, "God does not play dice with the universe." But experiments have repeatedly confirmed quantum mechanics predictions, and the theory has become the most successful and precisely tested theory in the history of science. Quantum mechanics underlies all of chemistry and solid-state physics. It explains how atoms bond to form molecules, how semiconductors work, how lasers function. Without quantum mechanics, we couldn't build computers or smartphones or understand how DNA encodes information. Yet we still don't fully understand what quantum mechanics means for the nature of reality. The measurement problem, the question of how and why quantum superpositions collapse when observed, remains unresolved. Various interpretations exist. The Copenhagen interpretation says the wave function collapses upon measurement, but doesn't explain what constitutes a measurement. The many worlds interpretation says the wave function never collapses, but instead the universe splits into multiple branches, each representing a different measurement outcome. In this view, every quantum measurement creates new parallel universes. If true, there are countless parallel versions of you, each experiencing a different outcome of every quantum event in your body and environment. The idea is mathematically elegant, but philosophically troubling. Do all those parallel universes really exist, or is the many worlds interpretation just a mathematical convenience? Here's a thought experiment for you. If many worlds is correct, and every quantum event spawns new universes, how many versions of you exist right now across the multiverse? Quantum events happen constantly, trillions upon trillions per second in just your body alone. The number of parallel universes would be incomprehensibly vast, growing exponentially with every passing moment. In most of those universes, you're nearly identical to the you in this universe, differing only in microscopic ways. But in some, quantum randomness led to different macroscopic outcomes. Maybe in some you made different choices, lived different lives. Maybe in a tiny fraction, quantum tunneling caused something highly improbable but not impossible to happen, like all the air molecules in a room spontaneously moving to one corner. These possibilities are so unlikely they might never happen in the entire history of our universe. But in an infinite multiverse, everything possible happens somewhere. Let's return to cosmology and discuss the ultimate fate of the universe in more detail. Current observations suggest the universe will continue expanding forever, driven by dark energy. As expansion continues, galaxies outside our local gravitationally bound group will recede beyond the cosmic horizon, the distance beyond which their light can never reach us due to the universe's expansion. In about 100 billion years, only the local group galaxies, Milky Way, Andromeda, and their satellites will be visible. Any civilizations arising after that point will have no way to discover the Big Bang or the expansion of the universe because they won't be able to observe distant galaxies receding. They'll think they live in a small, static universe consisting of a single galaxy in an eternal void. This should give you pause. What are we missing about the universe because of our particular time and place? What phenomena existed in the early universe but no longer occur? What observations are already beyond our cosmic horizon, forever lost to us? The era of stars will eventually end. In about 100 trillion years, the last stars will burn out. Star formation requires gas, and over time, the available gas gets locked up in stellar remnants like white dwarfs, neutron stars, and black holes, or gets dispersed too thinly to collapse and form new stars. The universe will enter the degenerate era, lit only by the faint glow of cooling white dwarfs and the occasional flash when two brown dwarfs collide and briefly ignite fusion. Even these dim lights will fade. In about 10 to the 40th years, the universe may enter the black hole era, where black holes are the dominant remaining structures. Protons, if they decay as some theories suggest, will have disappeared along with all atoms. Only black holes, electrons, positrons, neutrinos, and photons remain, scattered across a universe that has expanded to unimaginable size. The black holes themselves will eventually evaporate via Hawking radiation. A supermassive black hole containing billions of solar masses might survive for 10 to the 100th years or longer. But eventually, even these cosmic monsters will evaporate in final explosions, leaving only a cold bath of radiation in an ever-expanding void. This is heat death, the universe reaching maximum entropy, a state where no free energy remains and nothing interesting can ever happen again. Time becomes meaningless when nothing changes. But maybe that's not the end. Some speculative theories suggest more exotic possibilities. In the Big Rip scenario, if dark energy grows stronger over time, its repulsive effect could eventually become so intense it tears apart bound structures. First, galaxy clusters would be ripped apart, then galaxies, then stellar systems, then planets, then atoms themselves, the fabric of space-time torn to shreds. In the Big Crunch scenario, the universe's expansion reverses, and everything collapses back together in a reverse Big Bang, possibly leading to a big bounce and a new cycle. However, current observations suggest these scenarios are unlikely. The heat death scenario seems most consistent with what we know, but our knowledge is incomplete. Dark energy is poorly understood, and we're extrapolating trillions upon trillions of years into the future based on observations spanning just decades. We should hold these predictions lightly, acknowledging our ignorance. Let's talk about something closer to home: exoplanets. For most of human history, we didn't know whether other stars had planets. It seemed likely, but we had no proof. Then in 1995, astronomers detected the first exoplanet orbiting a sun-like star. Since then, thousands of exoplanets have been discovered, and we now know planets are common. Most stars have planets. The Milky Way likely contains hundreds of billions of planets, and many of those are rocky worlds orbiting in their star's habitable zone, the region where temperatures allow liquid water to exist on a planet's surface. Water is essential for life as we know it, so these habitable zone planets are prime targets in the search for extraterrestrial life. Some exoplanets are bizarre beyond anything in our solar system. There are hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun, their atmospheres heated to thousands of degrees, their years lasting just days. There are super-Earths, rocky planets several times Earth's mass. There are water worlds, planets covered entirely in deep oceans. There are rogue planets, ejected from their home systems, wandering the galaxy in darkness. There may be billions of rogue planets in the Milky Way, outnumbering stars. Imagine a world without a sun, forever dark and frozen, drifting alone through interstellar space. Life seems impossible in such conditions, but extremophiles on Earth survive in environments once thought incompatible with life. Could something live in the ice-covered oceans of a rogue planet, heated by radioactive decay in the planet's core? It's speculation, but not impossible. The discovery of exoplanets has transformed the search for extraterrestrial life from philosophy to science. We can now estimate how many habitable worlds exist and calculate the probability of life arising. The Drake equation, formulated by Frank Drake in 1961, attempts to estimate the number of communicative civilizations in the galaxy by multiplying factors like the rate of star formation, the fraction of stars with planets, the fraction of planets that are habitable, the fraction where life arises, the fraction where intelligent life evolves, and so on. The problem is we don't know most of these factors. We have a sample size of one for life, intelligence, and civilization: Earth. We don't know if life is common or rare, inevitable or a cosmic fluke. We don't know if intelligence is a likely evolutionary outcome or a bizarre accident. The Fermi paradox encapsulates this mystery. If planets are common and life is reasonably probable, the galaxy should be teeming with civilizations, so much older and more advanced than ours. So where is everybody? Why haven't we detected any signs of alien life? Various solutions have been proposed. Maybe life is common, but intelligence is rare. Maybe civilizations inevitably destroy themselves shortly after reaching our level of technology. Maybe advanced civilizations deliberately hide their presence. Maybe we're among the first civilizations to arise, living in a young galaxy that will fill with life in the future. Maybe interstellar travel is so difficult that even advanced civilizations can't spread across the galaxy. Maybe aliens exist, but we don't recognize their signals because they're too different from what we expect. Or maybe, just maybe, we're alone, the only conscious observers in a vast and empty cosmos. This possibility is perhaps the most unsettling, suggesting a tremendous responsibility. If we're the only intelligent life, then the survival and flourishing of human civilization takes on cosmic significance. Take a moment and ask yourself, would you rather live in a universe filled with alien civilizations, or one where humanity is unique and alone? Each option carries profound implications. A populated universe promises diversity and the possibility of learning from other intelligent species, but it also raises questions about our place in the cosmic hierarchy. Are we insignificant newcomers, or rare and valuable? A lonely universe makes us cosmically important, the only way the universe has come to know itself, but it also suggests a terrible fragility. If we fail, consciousness itself might vanish from the cosmos. Let's explore the possibility that we're not alone by examining the conditions for life. Life on Earth requires liquid water, a source of energy, and organic molecules. But is this universally true, or are we biased by the only example we know? Some scientists speculate about alternative biochemistries based on different solvents and different chemistries. On Titan, Saturn's largest moon, lakes of liquid methane and ethane exist on the surface. Temperatures are far too cold for liquid water, but methane is abundant. Could life based on methane rather than water exist there? It would be radically different from Earth life, with completely different biochemistry, but the laws of chemistry don't forbid it. Such life might be slow, its chemical reactions sluggish in the cold, but given the age of the solar system, it would have had billions of years to evolve. Similarly, some theorists have proposed life based on silicon rather than carbon. Silicon is chemically similar to carbon and can form complex molecules. However, silicon-based molecules tend to be less stable and versatile than carbon-based ones, so carbon seems better suited for life. Still, we shouldn't assume life must be carbon-based just because Earth life is. The universe is vast and diverse, and we've barely begun to explore it. Even on Earth, life exists in astonishing diversity and extremes. Extremophiles thrive in boiling hot springs, in ice sheets, in intensely acidic or alkaline environments, in the crushing pressures of the deep ocean, even in the radioactive waste of nuclear reactors. Life has been found miles underground, living in rock and consuming minerals. Some organisms can survive the vacuum of space, enduring radiation and temperatures that would destroy most life. Tardigrades, microscopic animals also called water bears, can enter a state of suspended animation, desiccating to less than 3% water content, and survive for decades in this state. They can withstand temperatures from near absolute zero to over 150 degrees Celsius, pressures 6 times greater than the deepest ocean, and radiation doses hundreds of times higher than would kill a human. If tardigrades can survive such extremes, what other forms of life might exist in environments we consider uninhabitable? Beneath the icy crust of Europa, one of Jupiter's moons, a global ocean of liquid water exists, kept warm by tidal heating from Jupiter's gravity. This ocean may contain more water than all of Earth's oceans combined. Similar subsurface oceans likely exist on several other moons in the outer solar system, including Enceladus and Ganymede. These hidden oceans are among the most promising places to search for life beyond Earth. We know life can exist in Earth's oceans without sunlight, sustained by chemical energy from hydrothermal vents. Similar ecosystems might exist in the dark oceans of distant moons. Future missions may drill through the ice and explore these alien seas, searching for life that evolved completely independently from Earth life. Such a discovery would be one of the most profound in history, proving life isn't unique to Earth and suggesting it may be common throughout the universe. The question of origins also fascinates. How did life begin on Earth? We don't fully know. The earliest evidence of life dates back about 3.8 billion years, not long after the late heavy bombardment when asteroids and comets heavily pelted the inner solar system. Earth's surface would have been inhospitable, yet life emerged quickly, geologically speaking. This suggests life might arise readily when conditions are right, or perhaps life's building blocks arrived from space, delivered by comets and asteroids. Organic molecules, including amino acids, have been found in meteorites and detected in interstellar space. The raw materials for life might be widespread, scattered by stellar processes across the galaxy. If so, the emergence of life might be less miraculous and more inevitable, a natural consequence of chemistry and thermodynamics. But even if simple life is common, complex multicellular life might be rare. On Earth, life remained microbial for billions of years. Complex multicellular organisms only appeared about 600 million years ago, after oxygen levels rose sufficiently. This oxygen came from photosynthetic bacteria that spent billions of years slowly terraforming the planet. The transition from single cells to complex organisms seems to require specific conditions and may involve unlikely evolutionary steps. Intelligence might be rarer still. On Earth, countless species have evolved, but only one developed technology and science. This could mean intelligence is an unlikely outcome, or it could mean it's recent and we haven't had time to see it evolve elsewhere. We simply don't know, and until we find other examples of life, we're groping in the dark, generalizing from a sample of one. Now let's turn to something truly mind-bending: the nature of space-time itself. We usually think of space and time as separate, three dimensions of space and one of time. But Einstein's relativity unites them into a four-dimensional fabric called space-time. Events in the universe don't happen at a location at a time. They happen at a point in space-time, a specific combination of where and when. Gravity isn't a force in the traditional sense. It's the curvature of space-time caused by mass and energy. Massive objects like stars and planets create wells in the space-time fabric, and other objects follow the curved paths around these wells. Earth orbits the Sun not because the Sun exerts a force pulling Earth toward it, but because the Sun's mass curves space-time, and Earth follows the straightest path through that curved space-time, which appears to us as an elliptical orbit. This conception of gravity makes predictions that Newtonian gravity cannot. It predicts time dilation in gravitational fields, which we've confirmed with precision atomic clocks. Clocks at higher altitudes, where gravity is slightly weaker, run faster than clocks at sea level. The difference is tiny, measured in nanoseconds, but GPS satellites must account for it or their position calculations would quickly become inaccurate. It predicts gravitational lensing, the bending of light paths around massive objects, which we've observed countless times. It predicts the precession of Mercury's orbit, a tiny anomaly that Newtonian gravity couldn't explain but general relativity predicts precisely. It predicts gravitational waves, now confirmed. And it predicts black holes, where space-time curvature becomes so extreme that it creates a one-way boundary. Relativity also tells us that simultaneity is relative. Events that appear simultaneous to one observer may not be simultaneous to another moving relative to them. There's no universal now, no cosmic clock ticking away the same time for everyone. Your now and my now only align if we're at rest relative to each other. This means the universe doesn't have a single present moment. Different observers slice the four-dimensional space-time into three-dimensional space and one-dimensional time in different ways, depending on their motion. What you consider the present moment on a distant star might be that star's past or future from another observer's perspective. This relativity of simultaneity is mathematically inescapable but philosophically troubling. It challenges our intuitive notion of time as a universal river flowing from past to future. Ask yourself, if there's no universal now, does the future already exist in some sense? Does the past still exist? Some physicists and philosophers argue for a block universe view, where all of space-time exists simultaneously as a four-dimensional structure, and the flow of time is an illusion of consciousness. In this view, your birth, your death, and every moment in between all exist equally, different slices of the four-dimensional you. The passage of time is just your consciousness moving along your world line, the path you trace through space-time. This view seems to eliminate free will, suggesting the future is already laid out, fixed and unchangeable. But quantum mechanics, with its inherent randomness, might preserve some indeterminacy. The debate continues, unresolved, touching the deepest questions of philosophy and physics. Let's discuss cosmic inflation in more detail. The standard Big Bang model had several problems. One was the horizon problem. Regions of the universe that are so far apart they could never have been in causal contact, meaning light hasn't had time to travel between them since the Big Bang, nevertheless have nearly identical properties, particularly temperature. How did they know to have the same temperature if they could never communicate? Another was the flatness problem. The universe's geometry is extraordinarily flat, balanced on a knife edge between positive and negative curvature. Why should it be so finely tuned? Cosmic inflation solves these problems. If the universe underwent exponential expansion in the first fraction of a second, driven by a hypothetical inflation field, then all the regions we now observe were in causal contact before inflation. They could reach thermal equilibrium, ensuring uniform temperature. Then inflation stretched space so rapidly that these regions became separated beyond each other's horizons. Inflation also naturally drives the universe toward flatness because any initial curvature gets stretched out, like wrinkles on a balloon that become less noticeable as the balloon inflates. Inflation theory makes testable predictions, and observations of the cosmic microwave background have confirmed many of them. The pattern of temperature fluctuations matches inflation's predictions remarkably well. However, inflation also leads to bizarre implications. If inflation started, it likely continues somewhere, forever. Space expands exponentially, but quantum fluctuations mean different regions stop inflating at different times. The regions that stop become pocket universes, like ours. But vast stretches of space keep inflating, spawning more pocket universes, which themselves spawn more in an eternal process. This is eternal inflation, and it implies our universe is just one bubble in an infinite cosmic foam of universes, each potentially with different physical laws and constants. We return to the multiverse, this time grounded in inflationary cosmology rather than quantum mechanics. The two multiverse concepts might even be related, different aspects of a deeper reality we don't yet understand. There's also the simulation hypothesis, the idea that our reality might be a computer simulation run by a more advanced civilization. This might sound like science fiction, but it's taken seriously by some philosophers and physicists. The argument goes like this. If it's possible to create convincing simulations of consciousness, then advanced civilizations might run many such simulations, perhaps to study history or entertain themselves. If simulations are possible and civilizations tend to run many of them, then the number of simulated consciousnesses would vastly outnumber real consciousnesses. Statistically, you're more likely to be in a simulation than in base reality. This argument has flaws and assumptions, but it's not easily dismissed. If we're in a simulation, the simulators might be able to pause, rewind, or edit the simulation. The laws of physics we observe would be the programmed rules of the simulation, possibly simplified versions of the true laws governing the higher reality. Some suggest we might look for glitches or optimizations in the simulation, like the quantization of energy or the speed of light limit, which could be computational shortcuts. But this ventures into unfalsifiable territory. If the simulators are competent, we might never detect evidence of the simulation, and the hypothesis becomes metaphysics rather than science. Ask yourself this: if you discovered definitive proof you're in a simulation, how would it change your life? Would it matter? Your experiences and relationships would still be real to you, even if they're patterns in some cosmic computer. Perhaps the question of simulation versus base reality is less important than we think, a distinction without a practical difference. Let's return to observable phenomena and discuss gamma ray bursts, the most energetic explosions in the universe since the Big Bang. These bursts release more energy in a few seconds than the sun will emit in its entire 10 billion year lifetime. They're so bright that we've detected them from over 13 billion light-years away, nearly at the edge of the observable universe. For decades, their origin was mysterious. Now we know most result from hypernovae, extraordinarily powerful supernovae from the most massive stars, or from collisions between neutron stars or black holes. When a hypernova occurs, if the collapsing star is rotating rapidly, it can form a focused jet of particles and radiation blasting out along the rotation axis at nearly the speed of light. If Earth happens to lie in the path of this jet, we see a gamma-ray burst. The explosion itself isn't more energetic than other supernovae necessarily, but the energy is concentrated into beams rather than spreading evenly in all directions, creating an intensely bright flash when viewed from the right angle. A gamma-ray burst in our galaxy, aimed at Earth, would be catastrophic. The burst of radiation could strip away the ozone layer, exposing the surface to lethal solar and cosmic radiation. It could trigger global cooling by altering the atmosphere's chemistry. Some scientists have speculated that a nearby gamma-ray burst might have caused one of Earth's mass extinctions, though evidence is circumstantial. Fortunately, gamma-ray bursts are rare, and the probability of one occurring nearby and aimed at us is very low. Still, the universe contains dangers we can't control, cosmic phenomena with the power to sterilize planets. Our existence depends partly on luck, on living in a relatively safe neighborhood at a relatively safe time. Speaking of neighborhoods, let's talk about the Milky Way, our home galaxy. It's a barred spiral galaxy, meaning it has a central bar-shaped structure made of stars, with spiral arms extending from the bar's ends. The Milky Way contains somewhere between 100–400 billion stars, along with vast clouds of gas and dust, stellar remnants, and likely hundreds of billions of planets. Our Sun is located in a minor spiral arm called the Orion Arm or local spur, about 26,000 light-years from the galactic center. We orbit the galactic center at about 220 kilometers per second, taking about 230 million years to complete one orbit. The last time we were at this point in our galactic orbit, dinosaurs were beginning their rise to dominance on Earth. One galactic year from now, the Sun will have evolved into a red giant, and Earth will likely be uninhabitable. The Milky Way isn't static. It's currently in the process of consuming several smaller satellite galaxies, ripping them apart with tidal forces and absorbing their stars. Streams of stars from these disrupted galaxies can be detected throughout the Milky Way's halo. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy. Despite containing hundreds of billions of stars between them, the galaxies are mostly empty space, and actual stellar collisions will be rare. But the galaxy's structures will be disrupted, their spiral arms scrambled, stars flung into new orbits. Eventually, the two galaxies will merge into a single elliptical galaxy, which astronomers have nicknamed Milkomeda. The night sky during this collision will be spectacular, with Andromeda growing larger over millions of years until it dominates the sky, a glowing band stretching across the heavens. Star formation will surge as gas clouds collide and compress. If humanity or our descendants still exist, they'll witness cosmic events of unparalleled grandeur. Let's zoom back out and consider the cosmic microwave background once more, this time focusing on what it tells us about the universe's shape and fate. By precisely measuring the size and distribution of temperature fluctuations in the microwave background, scientists can determine the universe's geometry. A universe with positive curvature is closed, like the surface of a sphere, and would eventually stop expanding and recollapse. A universe with negative curvature is open, saddle-shaped, and will expand forever. A flat universe is balanced exactly between these extremes and will expand forever, but with the expansion gradually slowing, asymptotically approaching zero. Measurements show the universe is flat to within about 1%. This is remarkable because any deviation from flatness grows over time. For the universe to be this close to flat now, it must have been extraordinarily flat in the early universe, fine-tuned to incredible precision. Inflation explains this by stretching the universe so much that any curvature becomes negligible, but it replaces one fine-tuning problem with another. Why did inflation happen, and why did it stop at just the right time to create a universe like ours? These questions touch on the fine-tuning problem mentioned earlier. The universe seems calibrated in multiple ways to allow for complexity and life. Change any of several parameters slightly, and you get a sterile universe. This has led some to invoke the anthropic principle. We observe these values because if they were different, we wouldn't exist to observe them. It's a tautology, but it's also true. In a multiverse with varying constants, we necessarily find ourselves in a universe compatible with our existence. But this doesn't fully satisfy, leaving a lingering sense that there should be a deeper explanation. Perhaps future theories will reveal why the constants have the values they do, showing they're not arbitrary but necessary consequences of deeper principles. Or perhaps the multiverse is real, and we simply got lucky, existing in one of the rare universes where complexity can arise. We don't yet know. Consider the anthropic principle more deeply for a moment. Does it make you uncomfortable to think our existence might be a cosmic accident, the result of parameters randomly falling within the narrow range compatible with life? Or does it fill you with wonder that the universe is structured in such a way that matter can organize itself into stars, planets, and eventually conscious beings capable of contemplating their own existence? Both reactions are valid, and perhaps the truth encompasses both. We are accidents in one sense, products of random quantum fluctuations in the early universe that grew into galaxies and stars. But we're also inevitable in another sense, the natural outcome of physical laws acting over billions of years. Given the right conditions, matter complexifies, forming intricate structures that process information and exhibit emergent properties like life and consciousness. We're made of stardust, yes, but we're stardust that woke up and looked around in wonder, asking where we came from and what it all means. Let's discuss one more exotic phenomenon: quasars. We mentioned them briefly before, but they deserve deeper exploration. Quasars are the luminous centers of distant galaxies, powered by supermassive black holes actively consuming vast amounts of matter. The material falling into the black hole forms an accretion disk, heated to millions of degrees by friction, emitting radiation across the electromagnetic spectrum. The brightest quasars shine with the luminosity of trillions of suns, outshining all the stars in their host galaxies combined. Quasars were more common in the early universe, when galaxies were younger and contained more gas to feed their central black holes. Most quasars we observe are billions of light years away, meaning we see them as they were billions of years ago. In the modern universe, most supermassive black holes have consumed the gas in their immediate vicinity and are quiescent, like Sagittarius A star at the center of our galaxy. But when galaxies collide and merge, gas gets funneled to the central black hole, potentially reigniting quasar activity. When the Milky Way and Andromeda merge, their central black holes will eventually spiral together and merge, possibly producing a brief quasar-like outburst. Some quasars exhibit jets, narrow beams of particles accelerated to near light speed, extending hundreds of thousands of light years from the black hole. These jets are powered by the black hole's magnetic field and rotation, though the exact mechanism remains debated. When a jet points directly at Earth, we see a blazar, a quasar that appears especially bright and variable because we're looking down the barrel of the jet, seeing its emission Doppler boosted and concentrated. Blazars are among the most variable objects in the sky, brightening or dimming by large factors over days or even hours as instabilities in the jet come and go. The universe also contains phenomena we've never directly observed but which theory predicts. Primordial black holes, for instance, might have formed in the first moments after the Big Bang from density fluctuations that collapsed under their own gravity before the universe expanded enough to prevent it. These black holes could have a wide range of masses, from microscopic to thousands of solar masses. Some scientists speculate primordial black holes could constitute some or all of dark matter, though this idea faces observational challenges. If small primordial black holes exist, they might occasionally pass through the solar system or even through Earth, their gravity creating detectable effects. So far, no such events have been confirmed, but searches continue. Another theoretical object is the white hole, the time-reversed version of a black hole. While black holes have event horizons you can enter but never leave, white holes would have horizons you can never enter, but from which matter and energy can emerge. General relativity's equations allow for white holes, but they're thought to be unstable and likely don't exist in nature. If they did, they'd violate the second law of thermodynamics by decreasing entropy, making them deeply problematic. Still, they appear in mathematics, and some speculate the Big Bang itself might be a kind of white hole, a point from which matter and energy erupted into spacetime. We've covered vast conceptual ground, but let's not forget the human element. Astronomy and cosmology aren't just collections of facts. They're journeys of discovery undertaken by curious minds across generations. Ancient humans looked up at the stars and created myths to explain what they saw, patterns and stories that helped them make sense of the cosmos. Early astronomers painstakingly recorded planetary positions, eventually realizing Earth orbits the Sun rather than vice versa, a revelation that displaced humanity from the center of the universe. Later generations discovered Earth is one planet among many, orbiting an ordinary star in the outskirts of an ordinary galaxy in a universe containing billions of galaxies. Each discovery diminished our cosmic specialness while expanding our understanding and inspiring new questions. The process continues. Every answer raises new questions. We've learned the universe is expanding, but we don't know why dark energy drives acceleration. We've detected dark matter's gravitational effects, but we don't know what it is. We've found thousands of exoplanets, but we don't know if any harbor life. We've observed the cosmic microwave background in exquisite detail, but we don't fully understand the first moments of the Big Bang. We've developed quantum mechanics and relativity, but we haven't unified them into a theory of quantum gravity. The edge of knowledge is where science lives, and beyond that edge lies mystery. Perhaps the most profound mystery is consciousness itself. How do arrangements of atoms give rise to subjective experience, to the feeling of being someone, of experiencing qualia, the redness of red or the pain of pain? Neuroscience has made tremendous progress mapping brain functions, but the hard problem of consciousness, explaining why physical processes are accompanied by subjective experience, remains unsolved. Some thinkers suggest consciousness might be fundamental, a basic feature of reality like mass or charge, rather than an emergent property of complex systems. Others propose it's entirely explainable in physical terms, and we just haven't figured out the explanation yet. This question connects to cosmology because we're the universe's way of knowing itself. Consciousness is how the cosmos becomes aware of its own existence. If consciousness is rare or unique to Earth, its loss would be cosmically significant. If it's common, springing up wherever matter complexifies sufficiently, then the universe might be filled with countless perspectives, countless ways of experiencing reality. Think about this. The atoms in your body were forged in stars, scattered by supernovae, collected into a planet, arranged by evolution into a form capable of thought. You're a configuration of stardust that can contemplate the stars from which it came. Every breath you take contains atoms that were once part of other people, other animals, plants, ancient microbes. You're connected to all of life on Earth through shared ancestry and shared atoms, and you're connected to the cosmos through your stellar origins. When you look at the night sky, you're not separate from it, looking at something out there. You're part of it, the universe examining itself. Let's close by reflecting on some of the most awe-inspiring facts we've encountered. The universe is about 13.8 billion years old, vast almost beyond comprehension. It contains at least 2 trillion galaxies, each with millions to trillions of stars. It's made mostly of things we can't see, dark matter and dark energy. It began in a hot, dense state and has been expanding and cooling ever since, creating space and time as it goes. Stars are nuclear furnaces that forge heavy elements, and when they die, they scatter those elements into space, enriching the cosmos with the raw materials for planets and life. Black holes warp spacetime so severely that not even light escapes, and they may eventually evaporate through quantum effects over timescales that make the current age of the universe seem like an eye blink. Gravitational waves ripple through space-time, carrying news of cosmic collisions. Quantum mechanics reveals reality is probabilistic and strange at the smallest scales, with particles existing in superposition until observed. Time is relative, running at different rates for different observers. Simultaneity is not absolute. The future may already exist in some sense, laid out in the four-dimensional block of spacetime. We live in a possibly infinite universe that might be one among countless universes in a greater multiverse. Life might be common or rare, and we don't yet know which. We might be alone, or we might be surrounded by alien civilizations we haven't detected. The universe's ultimate fate may be heat-death, a cold, dark eternity where nothing happens, or it might be torn apart in a big rip, or collapse in a big crunch, or something stranger we haven't imagined. Our knowledge is vast but incomplete, and every discovery reveals new mysteries. The universe is a place of wonder and terror, beautiful and indifferent. It created us through billions of years of cosmic and biological evolution, yet it could snuff us out in an instant through any number of cosmic catastrophes. It's so large we'll never see most of it, yet it's also our only home, the only place we know for certain harbors life. We're insignificant on cosmic scales, tiny sparks of consciousness in a vast ocean of space and time. Yet we're also significant, perhaps the only way this particular region of the universe has become self-aware. Our lives matter because we're here to say they matter, to create meaning in a cosmos that doesn't come with inherent purpose. As you go about your day, remember you're hurtling through space on a rocky planet orbiting a star in the outskirts of a galaxy that's falling toward other galaxies in an expanding universe. You're made of atoms born in the hearts of ancient stars. You're the current instantiation of an unbroken chain of life stretching back billions of years. You're a way the universe experiences itself. The same atoms that formed in the Big Bang, that condensed into stars, that fused into heavier elements, that scattered into space and collected into planets, are now arranged into the pattern that is you, reading these words, contemplating existence.